Between 2017 and 2018, targeted attacks known as Dark Vishnya cost tens of millions. The attackers bypassed perimeter security entirely, executing a precise, multi-stage physical intrusion. Step 1 requires physical entry. The threat actor enters the building, masquerading as a legitimate visitor, such as a courier or a job applicant. In Step 2, the attacker finds a discrete location and connects a cellular-enabled rogue hardware device directly into the local network infrastructure. For Step 3, the attacker leaves the premises. They establish a remote connection to the hidden device using standard 3G or LTE cellular networks. Steps 4 and 5 execute the digital compromise. With a foothold established, the attacker runs network scans, executes brute force attacks, and deploys malware from inside the local network. This split-screen timeline maps the attack's physical progression on top against digital network visibility on the bottom. Traditional security information and event management, or SIEM, systems monitor the network layer. Since the first 3 steps occur in the physical environment, SIEM logs remain flat. The digital alarm only triggers when the attacker reaches Step 4 and begins network scanning. By then, the network is already compromised from the inside. The modern SIEM architecture relies exclusively on digital traces. It possesses no mechanism to detect physical precursors to a cyber attack. The standard industry model treats employees as liabilities, the targets of phishing campaigns and the most vulnerable components of information security. But humans possess advanced semantic anomaly detection capabilities. An employee can recognize a suspicious visitor or identify an out-of-place router. Machines lack this contextual awareness. The current reporting mechanisms isolate this human intelligence. When an employee notices something strange and submits an IT help desk ticket, they generate unstructured, free text data. Standard natural language processing cannot extract reliable threat metrics from these tickets. The vocabulary is inconsistent, the context is ambiguous, and lacks rigid categorization. The engineering challenge requires translating unstructured human intuition into machine-readable cyber threat intelligence, or CTI. Bridging the air gap between human perception and automated CM ingestion provides the necessary data to detect physical precursors like Dark Vishnya before exploitation occurs. This architecture diagram illustrates the Integrated Human as a Security Sensor, or IHAAS, pipeline. Standard CM log aggregation sits on one side. The IHAAS module integrates on the other, connecting via push and pull pathways. The push vector activates when an employee actively submits event data into the pipeline. Unlike machine-generated logs streaming thousands of events per second, the human push vector delivers a specific, context-rich payload. The pull vector operates in reverse. A security analyst actively queries the employee network to extract missing context. If an analyst spots an ambiguous digital alert, such as a sudden bulk file transfer, they can use the pull vector to ask the local department if it was a scheduled IT task or an active breach. Both pathways introduce a vulnerability. Unrestrained human input will flood the SIEM with false positives, contradictions, and poorly formatted data. To function, the incoming data payload must be restricted and structured by a rigorous, hard-coded taxonomy before it enters the SIEM. The IHAAS taxonomy enforces 4 mandatory parameters for every report: threat sources, threat events, entities, and expected impact. The CM expects to ingest this data via industry-standard cyber threat intelligence formats, specifically STIX and CyBox. The limitation of the baseline STIX schema is its design. It is built almost exclusively to model active, digital attacks. This data tree represents the STIX schema. To capture passive, human-observed events, researchers mutated the schema, adding new XML nodes branching off the base entities. They created the structural source type vocabulary to specifically classify physical hardware threats. They added the environmental event type vocabulary to map passive contextual events occurring in the physical space. Expanding the vocabulary is only half the solution. The intake logic must enforce mathematical constraints. Constraints exist to block users from submitting impossible event chains into the database. For example, the logic dictates that an intentional cyber attack cannot be initiated by an environmental event. The system instantly rejects a user attempting to log a network scan as the direct result of a local power outage or severe weather. Combining these specific XML schema extensions with hard-coded logic constraints normalizes flawed human reporting into rigorous, queryable threat intelligence. We can run the Dark Vishya incident back, applying the IaaS pipeline to the target network. An employee spots step 1 and 2. They notice an unrecognized courier in the hallway, and later they find a small, unidentified piece of hardware plugged into an empty Ethernet port. This is the structured reporting wizard. Instead of a free text email to IT, the employee inputs their observation by selecting options from drop-down menus. The UI enforces the STIX vocabulary. The moment the user clicks Submit, the back-end server converts those selections. The output is a perfectly formatted STIX report object. The physical actions are automatically mapped to standardized KPEC attack patterns. The user requires zero knowledge of XML or CTI schemas. The user interface acts as a compiler, translating human intuition into SIM-ready mathematics. The STIX report hits the correlation engine. On our timeline, SIM visibility during the physical phases is no longer flat. It populates with structured human CTI data. The SIM now maintains active physical security context before any digital attack launches. When the attacker reaches step 4, they initiate the remote network scan from their hidden device. The correlation engine instantly matches the digital MAC address of the scan to the structural source report generated by the employee earlier that day. For the Security Operations Center analyst, the ambiguity is gone. They are not investigating an internal IP glitch. They have confirmation of a rogue hardware breach tied to a specific physical office. The defense is immediate. They completely sever the physical port connection before the malware payload can be deployed. The incident response team inherits pre-compiled forensic data, linking the digital footprint to the physical actor. By structuring human observations through rigid taxonomy, security teams pull the detection timeline to the left, neutralizing threats in the physical domain before they penetrate the digital one.